Okay, so building off of the last section, we're going to solve word problems involving rational functions, which seems like a kind of terrifying concept because solving rational functions are challenging, or rational equations are challenging enough in their own, but there's really only a couple of flavors that you're going to see. And so the first one is the work problem. And the reason that this is covered so often in math courses is that it seems like there's a deceivingly simple answer to these questions, but when you stop and think about what that answer is, you start to realize that there is kind of a hole in that logic. And so we have a situation where Mark takes 5 hours to paint a room, Steve takes 4 hours to paint the same room. So you might think, okay, well, it takes them 4 plus 5 hours to paint the same room together, so a total of 9 hours. That doesn't really make sense, right? Because if they're working together and they can paint it in either 5 hours or less, individually, they should be able to do better than that when they're painting it together. And so the other way to think about it is to kind of express what people are doing as a rate. And so if we say, Mark has, it takes him 5 hours to complete the job. Instead, we can think about it as an amount of job completed, because that is something that we can kind of add. If I finish one half of the house and you finish one half of the house, well, the whole house is kind of done. So we say that since it takes Mark 5 hours to complete the job, he completes at least the room. He completes painting 1/5 of the room in 1 hour. Same thinking for Steve. If it takes him 4 hours to complete the job, he will have completed 1/4 of the room once he is done painting for an hour. And that together, that they will be able to, we kind of have a variable there, we're going to call it X. But after 1 hour, we'll have the total amount of the job completed as well. And so when we express it like that, we can set it up as an equation. We find our LCD, which is 20x in this case, multiply everything by 20x, or at least all of the numerators. And then if we go through and cancel, 20x over 5 is 4x, 20x over 4 is 5x, and 20x over x is 20. So I can add the 4x and the 5x together, divide both sides by 9, I get 20 over 9. Now, if someone asked you this question in the real world and you said, oh, it takes them 20 over 9, you'd probably get a puzzled look. So we have to go that additional step and express it into terms of that someone in the real world would understand. And so I wrote it kind of mesh between in too mathy and not mathy enough, which would be 2.22 hours. Generally, people would probably even prefer, not mathy enough is not a good term for that, but people generally would like it as minutes, hours and minutes. So then you would just do 0.22 times 60, since it's 60 minutes in an hour. If you want to go that additional step, that's fine. I wouldn't make you do it, because then I'm making you do a word problem with rational equations and then making you do a conversion at the end. But I do want some sort of real answer. So I don't want it as a fraction. I definitely don't want it as a fraction with no units in it. And so I'll take the compromise a number with a decimal and then have hours attached to it. Now that question and this question is kind of related to these 4 formulas. The first one shouldn't be a shocker to too many people. Distance is equal to rate times time. And then to find my time, I could do distance divided by rate, or distance divided by time would get me my rate. So we have an equation here of a tugboat, or sometimes it's people rowing, or maybe it's a speedboat or something. Not really important, but they're on a stream. We could also honestly have a plane flying and have a very similar type of problem. But in this case, we have a tugboat. We know that it takes 1 2/3 times as long to go upstream as it does to go downstream, because it's fighting a current. So that's why I was saying we could do this with an airplane as well. Sorry, it's always so loud. We could do this with an airplane as well, because you have airstreams kind of slowing things down or helping you along the way. And so from there, we know that the speed of the current is 2 miles per hour. We want to find the speed of the tugboat in still water, which would mean that it's kind of traveling at the same rate on its own if there wasn't a current there. So like you pretend kind of taking the boat out of that and saying, okay, well, what's its miles per hour if it just was sitting on a nice little pond with no current involved. So that's what it means, but really we just need to find the speed of the tugboat, not to overly confuse ourselves. Here we have to represent our variables. And so the information that we have is we have the speed of the current, we have the speed of the boat, we don't have the speed of the boat, we're looking for the speed of the boat, and we have distance. So the speed of the current is 2 miles per hour. The speed of the boat, we're going to just declare it as an x, and we know that the distance up and the distance downstream will be 100 miles because it's a river. Unless you're taking a weird route downstream or something like that, it's going to be the same distance both ways. Now looking at this, I kind of see that I am trying to find a rate. And so of the three equations at the top, the first one, it helps me find distance, the second one helps me find time, the third one helps me find rate. So I'm going to use the third equation when building my overall rational equation to solve. Now I put all of the information that I have into this table. So the top row of my table is my upstream information. The bottom row of my table is downstream information. I know the distance is the same for both, it's 100. I know the rate for upstream is going to be, I'm fighting my current upstream, so that's going to be x minus 2. And the current is helping me downstream, so that's x plus 2. And now I can figure out what my time is by doing distance divided by rate, looking at the second equation above. So I have my distance is 100, my rate's x minus 2 for my upstream, so that's 100 over x minus 2. Very similar reason for the second row. My time is going to be, I think I said rate. My time for upstream is 100 over x minus 2. My time for downstream is 100 over x plus 2. Hopefully that didn't super confuse a lot of people. I apologize. Now I know the only piece of information that I'm missing from my problem is I haven't really talked about that 1 2/3 times as long. Now to account for that, what I'm going to do is I'm going to first change that into an improper fraction because it's kind of hard to deal with as a mixed number. And I know that my upstream, that's probably going to be my slower time because I'm fighting current versus my downstream is being helped my current. And so my upstream is 5/3 time as long as downstream. So if you remember kind of converting word problems, that is going to be an equal sign. So I have my upstream time, 100 over x minus 2, is going to be equal to my downstream time, which is 100 over x plus 2, times 5/3, 5 over 3. And so 100 over x plus 2 times 5 over 3 gets me 500 over 3. Now to find my LCD, I look at my denominators. I have x minus 2 on one. I have x plus 2 times 3 on the other. That leaves me with my LCD, 3 times x minus 2 times x plus 2. And now I'm going to multiply everything by, well, not everything, every numerator by my LCD. That leaves me with, on the left fraction, 100 times 3 times x plus 2 times x minus 2. On my right fraction, 500 times 3 times x plus 2 times x minus 2. And now I can go through and cancel like terms. On my first fraction, I can cancel out my x minus 2's, and that's about it. And on my second fraction, I can cancel out my x plus 2's, and I can cancel out my 3's. Once I've done all of that canceling, I will be left with 100 times 3, which is just 300. 300 times x plus 2, and 500 times x minus 2. If I distribute out, I get 300 times x plus 2. And if I multiply out, I get 300 times x plus 600 and 500 x minus 1000. And now I can add 1000 over, add it to both sides, and then I get 1600 on the left side. I subtract 300x from both sides. I get 200x on the right side. I divide both sides by 200. I get x is equal to 8 miles per hour. Now, it's very important in word problems. I'm sure I have in the past, if I haven't multiple times, already mentioned that once you get to that last step, you should check to make sure that your answer makes sense. So I should have done that on the last slide too. But in this case, I know, especially when I was teaching this the first, honestly, 10 times, when I was setting up that equation right under the upstream is 5/3 time as long as downstream, I wasn't sure which side to multiply 5/3 by. And honestly, sometimes the best strategy is just to try one and then go through your whole process and see, does your answer make sense? So in this case, if you did 5/3 on the wrong side of the equation, you would get to the end and you would get x is equal to negative 8 miles per hour, which doesn't really make sense. So that's the little pause that I want you guys to do anytime you're doing a word problem, is two things once you're finished. I want you to make sure you do units or be able to kind of give a real world answer. And then the second thing I will want you guys to do is look at the answer and think to yourself, does that make sense? And in this case, maybe you don't really know a whole lot about tugboats. I honestly don't myself, but I know that it's not negative. I know that tugboats, my answer is not something crazy like 1,000. So 800 seems pretty reasonable, all things considered. And if I really wanted to do a check on this, I could figure out my time by plugging in my x. I would multiply it by my rate, and then I should be able to get back 100. So that's kind of the math way to do it, but really I want to kind of just have that logic check. That's a very, very powerful thing in mathematics that I feel like isn't talked about enough.